Welcome, everyone. Thank you for joining us today to Graph Gurus 23 on best practices for modeling your data with graph. We just opened up the webinar, so probably people have not had it. Oh, we've got 20 people joining so far. I'm sorry, we opened it up a bit late today. So I'm Victor Lee. I'm head of product strategy and developer relations at TigerGraph. And with me today is Xinyu Chang, director of customer solutions. And today we're going to be talking about the best practices or ways to optimize your modeling your data with a graph. Or if you have a graph, what's the best way to model your data? So some housekeeping items. Your sound is muted, but you can ask a question through the Zoom app with the Q&A. So there's both Q&A and chat. So if you have a formal question about the content that you would like us to answer, please use the Q&A. If you have something procedural like some technical difficulty or anything else that where you maybe actually want to have a more informal question, you could try the chat. But for things that, you know, we'd actually like the whole group to hear, and like Q&A at the end, we will have a Q&A section at the end. Please use the Q&A tab. The webinar is being recorded. So if you're not able to stay for the whole time, or if it turns out you're not even with us live, we'll be sending you the recorded version. And so if you do have any questions, again, let us know through the chat. So I'm going to start with giving you a background to say what our views are on data modeling and why it's relevant for using a graph database well. That's how and why it matters. And then Xinyu will be going into some specifics about some different techniques. It has about 7 different considerations and techniques you can use. So first of all, what is data modeling? Data modeling, it's the first step in making sense of your data. You're organizing it. You're figuring out, rather than just having this random blob of things, what types of things do I know? And what are they about? And then, so once it's organized, then you can start to draw information and knowledge and insights out of that data. So a really common approach is entity relationship modeling. And one website even defines ER modeling as a graphical approach to database design, which is great because even though they weren't talking about graphs, they used the word graphical. And there they meant more just visual. And that's important because we actually, that is one of its great strengths, the human side of it, that it makes it easier for us to understand the data. But it also makes it easier for the computer to understand the data. And so we want to take advantage of both. So the basic ER modeling technique, it's really, remember, it's a tool. It's not, it's designed to help you as well as the computer. So ask yourself, what are the fundamental things or objects or entities that are the core constituents of your data? What is your data concern itself with? Do you have people? Is it a social network? Or you know, whether the types of relationships are social relationships, whether it is an employee or student database, they're people. Are you concerned with products? Are you concerned with processes? Are you trying to detect fraud? What sort of data do you have? So what are the things? And then start to describe those things in a little more detail. What are their properties or attributes? You know, you can list individual things like, okay, that thing is heavy and it's brown. And then you realize, oh, that's weight and color. So weight and color are properties. And then what are the key relationships between your entities? And again, so when I was talking about social network, obviously you're concerned with social relationships. Somebody knows somebody else. You may be able to refine that into more subtle types of relationships. In a workplace, you have employee to supervisor relationships. In a school environment, you have both students who are taking classes, instructors who are teaching classes. You have people are organized into departments. And they're all, again, you also have the work relationships also there. So there can be many different types of relationships. You have dependencies. You have components and subcomponents in a supply chain. You have delivery, all sorts of possible relationships. And then you want to make sure that what you're doing is you're thinking about categories and classes. So just like I said before with properties, you can start to enumerate individual properties, like this thing is heavy, this thing is brown, and then but you realize you want to generalize that into a category, into talking about weight, talking about color. And the same thing, you can do that also with the entities. List the individual entities, and then you start to realize, oh, those are all falling into a certain category. So identify those categories of entities, properties, and relationships. And so you realize, hey, those entities, those are like nouns, properties are like adjectives, and relationships are like verbs. So you can often express these things as sentences. Like, for example, a student enrolls in a class, or instructor teaches a class. So student, instructor, and class are entities, and enrolls in, teaches, those are relationships. So I know a lot of you know this already, but the reason why I'm going over this is I want to identify what we're going to be focusing on. So this is the focus, looking at the ERs and properties. And because those have direct corollaries to graphs. Here are two common styles for visualizing ER models. On the left, you have the tabular style, and on the right, you have the style that breaks everything down into individual entities, where even the properties are the reddish ovals. And so you realize, particularly the one on the right, looks a lot like a graph. And so that's perfect. So what you have is a graph database, we're going to design a model that is itself a graph, but it's sort of the meta description of everything that's within the graph. So, when you look at the diagram here, what you're seeing is one of each thing. So there's one character with a contains relationship to a region entity. And so in your actual database, you may have hundreds or millions of characters and, hundreds or thousands of regions, and then, millions of relationships between character and region. The schema shows you one of each thing, one of each possible type of relationship or property ownership. So we recognize that these ER models are graphs. When you're doing database design, this model can also be called a schema. So you see that terminology come up. So we're going to start referring to them as schemas. And in a database, there are a couple ways. I see three possible ways that a database can use a schema. The first is the schema first approach. So you define your schema. And then when you bring in data, and therefore all the data conforms to that predefined schema. And that has many advantages, which we'll go over with you next. A second is the opposite end of the spectrum, no schema. So each individual entity has its own properties. So you just, rather than focusing on the categories, there are no categories. Just here's a thing, here's its properties, and you have ad hoc relationships. You can create any relationship you want. Now, in reality, you'll tend to have categories whether you've explicitly stated them or not. And so the data itself will tend to have some inherent categories, as I said. It's just that you have not explicitly stated the model and you're not requiring the data to follow that model. And lastly, there's hybrid, where you have a schema, but you're not requiring the data to apply it. So, you can call it you could call it weak conformance, or there's a range here. So just like we have a spectrum, schema first, and all data must conform to the schema, or no schema, and you can pick somewhere in between that works for you. Oops, sorry. So let's look at the category of schema first databases. That includes all relational databases. So ER modeling was really developed around relational databases, and they are schema first. And the Tiger Graph database is also a schema first database. So first of all, it clarifies your understanding. Again, the ER model is designed to be both a human aid and a computer aid. So by thinking about the structure of your data ahead of getting too deep into it, you have a clearer idea of what you're trying to do. As we said, it also enforces data consistency. So all the data you know satisfies that data model or data schema. So it's already performed some data cleansing for you or data filtering on the front end. Third, it simplifies query writing. You don't have to, often you might not have to specify the nature of a relationship or the nature of the entity because it's kind of already known. Like if you think about this event connecting to a tag, well, event connects to two different things, but you don't have to name that relationship. You don't have to say it's the have relationship because you know what the relationship is between event and tag. It's have. Or you know what the relationship is between event and company. Or you can also think of it as some of that type checking is performed automatically by the query for you. So when you refer to an entity of a company, you know what the properties of the company are. So you can depend upon that. That provides some guarantees. It can, and depending on the particulars of the query language, that could do some things for you automatically. So it simplifies the query writing. Something you might not realize, it also improves data sharing and access control. Because things are clearly defined and put into categories, you can say, oh, I want to share this category of data with another person. And you can just simply name the category. If you have no schema, you have to name individual instances, which can be a real big burden. In the same way, the flip side of data sharing is access control. Looked at one way, you're allowing people to see something. The flip side is you're not allowing other people to see that. So that's, again, two sides of the same coin, data sharing versus access control. And the last point, and the one that Xinyu is going to focus on, is how it enhances query optimization. So based on how the data is structured, there are some implied performance issues, and the more you understand the nature of how your database works, the more you're able to optimize your queries. And looking at the data model is one of the first steps to understanding how your database works. So, as I said, I've concluded my part, and now we're going to let Xinyu talk about some best practices in data modeling for graphs.
Okay. Victor, can you let me share my screen?
Sure.
All right. So I would talk about like the best practice in designing the schema of Tiger Graph. So usually when we want to design the schema, we take two things into the consideration. The first thing is that the format of your input data. That means that we cannot define an edge utilizing columns across the data files, right? So the from ID and the target ID of an edge has to be stays in the same file. So that means your schema is highly based on your input data format. And the second thing we want to consider when we design the schema is the query use case. Okay, we want the schema serve the best performance of the query, right? We want to like change the schema to make the query runs faster or use less memories. Okay, so in my talk, I will cover a whole list of topics on what is the best practice to design the schema for different scenarios. First of all, I want to talk what can be vertices and what can be edges. So it's actually very intuitive. The entities or abstract concept, they can be defined as vertices. It can be a person, a user, company, account, product, an address. They all can be like vertices or phone number, device. And you can also be a concept like types or status or and so on, right? So relationships, they are all kinds of relationships. They can be defined as edges. It's like two employees, they are coworker. Like one employee works for another company. One company is controlled by another company. All these type of relationships, all of them can be defined as edges in the graph. So this is like a visualization, like how vertices can be connected to each other through some edges, right? So when we define the schema, the first question we usually ask ourselves is, because we have three choices for the edges, right? Undirected edge, directed edge, and directed edge plus reverse edges, right? So when we define an edge, the first question we want to ask ourselves, which one should I choose, right? For example, the undirected edge is like A can traverse to B, but B cannot traverse back to, can also traverse back to A. That's undirected edge. There's no direction, no information stored on the edge. Therefore, it's undirected edge. And also we have directed edge. That is, A can traverse to B, but B cannot traverse back to A, right? That is, B is in A's neighbor, but from B, we cannot see A anymore because no edge pointing to A from B, right? So that's directed edge. And also we have a third choice, that is directed edge plus reverse edge. That means from A, I can traverse to B through edge E1, and from B, I can traverse back to A through another edge type, that is E2. And in this case, E1 and E2, they are symmetric. So E2 is created automatically when we populate the edge E1, right? So these are the three choices. Okay, so how do we make the decision? So each choice has its own pros and cons, right? For undirected edge, the advantage is it is very simple to work with those undirected or bidirectional relationships. Like A is friend of B. It's something like a Facebook friend, right? There's no direction. So A is friend of B or B is friend of A. There's no direction there. So it's recommended to use an undirected edge in this case. But the problem is it does not carry any directional info, and it will limit your traversal capability in certain scenarios. And we will talk about that in later slides. And for directed edge, the advantage is it saves memory because you only store the edge once. You only store the edge for A. You don't have to store any edge for B, right? And the problem is you cannot, if later, okay, you figured that we do need to traverse from B to A, then there's no edge that you can direct you from B to A anymore, right? So we really need to think it through before defining any directed edge. And here is our third choice. The advantage, the process is very flexible to traverse in either direction, right? Because I can feel free. If I want to go that direction, I use E1, the other direction, I use E2. It's very flexible. The cons is you need to maintain or remember two edge types. Okay, give you a harder time when you write the queries. Okay, so now let's talk about this is the advantage of undirected edge. See, for example, if we have a schema that is user has email, right? So in this case, if we define the edge as undirected edge, then our traversal select statement is very simple, right? If I want to find the user who shares the same email, I just repeat this edge using this edge twice. Then I can find all the users share the same email. However, if I do it with a directed edge and the reverse edge, then the select statement has to mention two types of edges. Therefore, the traversal is less concise. And here we may also ask, can we just use directed edge? The answer is no. If we have directed edge pointing start from the user to email, then we cannot find all the other users who also use the email because the edge is directional, right? So this is one of the advantage of undirected edge. But in some cases, we cannot use the undirected edge because it doesn't provide you the directional info in the graph. For example, this is an enterprise graph. Okay, so that is one company is another company's parent company. Okay, so in this graph, we want to ask a question. For example, given vertex C4, which company is his ultimate parent company? Then we need to start from C4, traverse all the way up to the root of the tree in order to find the ultimate parent company. However, if we define the schema with undirected edge, in this case, we just cannot do that because from C4, we don't know which one is a subsidiary or parent company. It is not, there's no info like that in the edge, right? So in this case, it's definitely recommended to do it with directed edge with reverse edge, right? So here, the red edge has parent edge. Blue edge has subsidiary edge. Then if we want to find the ultimate parent company of C4, then all you need to do is just to utilize the red edge and traverse all the way up. If you want to find all the subsidiaries, you just use the blue edge to traverse all the way down, right? It's very easy to do it with the directed edge, with reverse edge. So that's the key difference between the undirected edge and the third choice, directed edge and reverse edge. Okay, this is how we make the decision to choose between the three. And once the edge is defined, we may have another question. So in this example, people can be related in a lot of different relationships. Like a two-person can be co-workers. They can also be relatives. They can also be friends. There are many relationships can be among the people, right? So in this case, we do have two choices. That is, we can define specific edge type for each relationship type, right? Like the left-hand side. Also, we can also define a unified edge type, like say it's related to, and store the relationship type on the edge as a string, right? So there are different pros and cons in different approach. Like on the advantage of option one is it is very efficient when you traverse a specific type. If you want to get all the coworkers of a person, then it's very, very fast because you only use this subset of edges, right? But if you do it with the schema on the right-hand side, you need to scan over all the edges in order to find who is his coworker. However, if you want to traverse all the relationships belongs to one person, then it's less concise. You need to mention all the edge types in your traversal, right? Also, on the with the approach of the right hand side, the problem is you also need to use extra memory to store all the relationship types. But if you want to just traverse all the relationships, it's very easy. Okay, and the next topic, and another question to ask is, given the column, a non-primary ID column in your input data, should we create a vertex, or should we just leave it as an attribute on the vertex? Right. For example, we have a product table having the product's color, brand, type, and price. So, for the last 4 columns, should they be just an attribute like this, or we can define them as vertices? So that is the question. So if we define them as attributes, then if in your query you have to frequently query for the color of the product, then each time you need to scan over all the vertices in order to find the selected attribute. It's very time consuming, right? And if you do have queries that they frequently query for some attribute, so here the best choice here is we can create vertices for those attributes. For example, we can create a vertex type like a brand, vertex type as a color, and vertex type of product type. Then in this case, if you find give me all the red products, you just want to start from the red color vertex and find all the products that are associated to the red color vertex, and then you get all the red product. Then it makes your query a lot more efficient in this way. However, if you don't have to frequently query for this attribute, then maybe more likely you just leave it as attribute on the vertices. Okay, and the next topic we want to discuss is how to model time in graph, right? Because everything is graph. We can also create vertices for those. We can create a vertex for a year. We can create vertices for a month. We can create a vertex for any period of time, for 5 minutes, for 15 days, right? And also we can make this structure hierarchical, because so the advantage of doing this is if you want to query for a specific date, like the first 15 days of February 2018, then you traverse a lot less vertices than you have to when you just store the date on the vertices, right? So in this time, it's very, it's like we're creating an index for the dates to accelerate your query speed, okay? And also, we can create those a hierarchical structure for a BOM graph, for product attributes, or even for locations. And we can connect the inventory or the entity that are having those attributes. For example, in this example, we have BOM graph, we have product attributes, and we also have a location. So then with this structure, we can ask all kinds of questions. For example, we want to say, okay, give me all the inventories that is material of car rims, and also the color is under color gray, and is produced in USA. Right? Then we can just start from this vertex, this vertex, this vertex, and traverse all the way down to the tree and find all the relevant inventories. So in this case, in this design, it gives you very high flexibility in the searching conditions. It can give you everything that is the descendant of your input searching conditions to give you all the relevant inventories. Right? So a lot of stuff can be hierarchical. For example, it can be the company's organization chart, different departments, right? And here it's a hierarchical structure of locations. Like USA is a child node of North America, and California is a child node of USA, and Rose City is a child node of California, something like this, right? And in this case, like we have 4 type of vertices, but we may have like a 1, 2, 3, 4, 5, 6 type of edges. And these are the edges connecting between the like a parent-child relationship in your hierarchical structure. And also each inventory can have some attribute. Each of you utilize one edge, right? Okay. And here is also a very frequently asked the question from the customers. So that is, if my graph is event or transaction based, right? For example, 2 users can have many transactions. How should we define the graph, right? So here we have 2 choices. The first choice is we can define the transaction or event as vertex, so that like the users would connect to all the transactions he did before, and the transaction connects to say this is a receiver of that transactions, right? We have a transaction between the users who had the transaction. And another choice is we can also store the aggregated info or all the info in container on one edge, right? Which directly connects the 2 users that had the transactions before. Since the transaction can be multiple, then we can store some aggregated info. Like the last time they did transaction, first time they did transaction, the total transaction amount, right? And I can also store all the transaction dates in a list on the edge as an attribute. So these are the 2 choices. So what are the pros and the cons of the 2 choices? So the first approach with transactions in between, the pros is very easy to do transaction analytic, such as find the transaction community and identify similar transactions. And you can also just do the filtering on the transaction vertex attributes. Then it's very easy to do that. However, the cons is it will use a lot of more memory because we are creating a lot more edges and vertices to maintain the transaction vertices. And it takes 2 steps to traverse, like a given the sender to get the receiver, it takes 2 steps because we need to get to the transaction first and then get to the receiver, right? And for another approach, the pros is like it uses significantly less memory, and it takes fewer steps to traverse between users because they are directly connected. It's very convenient. But the problem is the searching on transaction is less efficient. If you want to like search for, I want to get transactions between certain period of time or within certain window of amount, then it's a lot less efficient because you need to scan over all the edges to find those transactions. And it becomes slow when you when you have to maintain the containers stored on the edge. That's another concept of that. Okay, so we usually based on the decision, we make the decision based on your like a specific use case. It's like you do want to do like a more transaction analytic, you choose the method on the left. If you want to like directly be able to locate to find the receivers of a sender, then you just choose the schema on the right, right? It's case by case. So other than those, we also have like a derived edges. The derived edges or vertices, they doesn't exist in your input data. So those are generated by running the analytical query. And once they are populated, you can use it for all kinds of further analytic and the calculations. It will accelerate your future analytic. Okay, so in this case, it's how we build a referral network. Because in our input data, we don't have this referral relationship at all. So that type of relationship is calculated and populated in with a query through some analytic, right? So that means a referral relationship will be created once one patient has 2 consecutive claims with 2 different doctors. Then we say, okay, these two doctors are related, they refer to each other, right? And with this referral edge, you can do like around a page rank. Then you can find the most influential doctors in the network, right? And we also, and the examples just can be goes on and on. Like we can also create like a household in your entity resolution network. It can be a lot of stuff. So the point here is the some of the edges, they are not from your input data, but they are derived from the analytic. You can also include those as part of your schema. And so here we want to talk about how do we design the schema based on your own use case. Okay, so so in given this table, it's kind of like a system event table. It has the event ID, IP address, server, device, user ID, and event type and message, right? So given this table, the set of edges we can define is infinite, right? We can define a lot of edges and vertices. The choice of schema is also a lot. So how do we make the decision? Do we do it like an IP centered, which doesn't make many sense, or we make it event centered or user centered, right? Each choice has its own like pros and cons, and we want to make this decision based on your own use case. For example, if we define the schema like it's event centers, that is the event vertex lies in the middle and it connects to everything relates to this event. The pros here is all info of event is in one hop distance. If you query anything about an event, you just do a one hop traversal and get everything, right? And the cons is if you want to find the IP being used by the device, then it's two hop away, right? So with this design, the suitable use cases are if you want to find the community of events, or you want to find the servers that process the most events of a given event type, because they are just one hop away, right? Or you want to find the servers visited by the given IP, then it's also very easy just to hop here. Or we can define it as user-centered schema. User-centered schema, the process is very easy to do analytic between two users, because you say you want to ask questions. Okay, I want to, given this server A or user A, I want to find all the similar users. Then you just find the users who shares the same set of neighbors, right? And the cons is now the events are too hop away from each related server or IP, and we cannot tell like which the IP is used in which event with the device, because they are not connected to event anymore. We don't know when this IP is used, what device is together with that IP in that event, right? We lost that information in this design. But in this case, the suitable use cases are if like you want to start from a input user, you want to find, okay, you detect the blacklisted user in K hops, right? To do like an anti-fraud user. Or you can given a set of blacklisted user, identify the whitelisted user similar to them. Or you can given two input users, ask questions like, are they connected in some sort of path? That is also a very suitable use cases for the design on the left. So all in all, the point here is we always design the schema that make it the most suitable to your use case. That means make your query runs fast, make the system resource consume less, something like that. And that's my part.
Okay, thank you very much, Xinyu. So I think that was a very helpful discussion, and I want to also thank everyone for joining us today. We know your time is precious, and we've had a record attendance to this webinar, so we really appreciate your interest. We are open for your questions. There was a question earlier about how we do geographic information. I think Xinyu tried to answer that, and I hope that was covered. We have one more question so far. So you mentioned these are best practices. So what if I started with a certain schema and then later realized that I want it a little differently? How can I change it?
We support dynamic schema update. That means you can change the schema, make changes to the schema without stopping the services. However, for some of the edges, if you you change is from or target vertex type, then in that case you need to re-ingest the data. But you can always make the change.
Okay, and so far we have 8 more questions from our audience, so we'll see how many we can handle. The first is, what's the best way to handle multiple different languages? So I'm assuming they mean that the data. So I guess there are 2 possible meanings, and I'm wondering if they mean, okay, the data is mixed, or you actually want to break it up, categorize it by language. But I'm going to assume it's just mixed. Well, I assume actually they want to categorize it. So if you wanted to categorize different attributes by language, I would think that's a modeling issue, that you would somehow say, okay, here are the English attributes, here are the Spanish ones, here are the Chinese ones. You could just do that by name. Do you have any other suggestions, Xinyu?
Right now, the schema can be only defined like in English.
So you mean the types, but I'm thinking about the types, but the values. The values we just
Oh, so what value supports like we support like a UTF-8, so you can use like Chinese character, Japanese character. I think we cover most of those.
Okay, so now a person has a specific question about setting up different types of person-to-person relationships. I'm not sure if you can see the question, because it's kind of specific. So we have a person is relative, person is friend, person related. So that's very close to person is relative. But so that would be different types of edges corresponding to different relationship types. So I think what they're saying is, so first of all, that's the general problem. They have different types of relationships. Can you speak to that?
Yeah. So let me try to understand the question here. Yes, in that case, yeah, we have 2 choices. Like we discussed here, right? We can have like a multiple different type of edges and each has different pros and cons.
Oh, I think they were maybe asking you to explain the one on the right a little bit better. Sort of translate the one in the left into how do you do that on the right?
Oh,
So what is in that relation type string?
oh, that relation type string is like if the 2 person they are coworkers, then there will be a string stored on the edge, like has value is coworker.
Right. So there's a generic relationship, and then the string tells you which of these 3 or 4 different types it is. So that string value could be coworker, or relative, or friend. So the person was asking whether we can have an edge coming out of an edge. And I would say, first, that doesn't seem to be really necessary here. So I would say that's not really the best solution to this problem, having an edge on an edge. So in general, property graphs don't support that. There's another question. Would hierarchies, and I think previously you had some other slides that showed sort of a hierarchy. would they correspond to dimensions in a relational star schema? And so you're familiar with like a star for people that are familiar with star schemas, which were commonly used in like data warehousing. So you have, and this is with curated data, so you would have sort of a hub entity which is drawing data from different dimensions. And so the different dimensions sort of follow different themes, and they kind of reduce to one type of information in the hub. Um, I think that's, I think what Shinyi was saying, that's one possibility here. But of course, the graph is more flexible than the star schema. The star schema was fitting, basically working from a relational approach, and this is more open ended. So it's not as it's not forced to follow the strict nature of the star schema, but of course it can be used that way. Fourth question, in the bill of materials example where you are, what would be the use of the color node when you need to specify the colors anyway? Are you planning to create labels to represent taxonomical relationships, such as color in the future roadmap? So I think they're asking, what's the difference between having a color node, and I think this is getting to the difference between the schema graph and the data graph. So maybe you could kind of go over again the difference between color in the schema versus particular colors in the data.
Color in the schema, you mean?
So first of all, what we're looking at here is a schema graph.
Right.
Oh, I see this hierarchy.
Uh,
So,
they, yeah, these
they're
are
asking,
the.
why like these are particular colors as types, as no. So I guess the questions are these data nodes or schema nodes?
Oh, those are data nodes.
Okay,
And the vertices under the same color, they are the same. They are under the same type here.
so is everything here a data node?
Yes, like all the green ones are under the like say attribute color. That is the color vertices. They are under the same type. All the yellow ones, orange ones, they are under the bomb type. Yeah.
Right. And so I guess the person was trying to ask, if we have these specific values, why do we explicitly create this hierarchy? And I think you did explain that, but maybe, so why not just have the bottom, the leaf nodes? What is the value of these? And maybe you could explain that again.
Oh, yes, of course. The reason is if we want to search for all the gray products, but on the attribute value, it might be like a light gray or dim gray. It doesn't match, right? So then we can just start from the gray vertex, find all the like the descendant gray colors, and then find all the inventories under those lower level gray colors, right? And it is the same way. If I want to find all the products in USA, but in the actual attribute, the value might be Revu City, right? Then we can just start from the USA vertex and find all the cities there, and further find all the inventories inside the USA.
Okay. So it's basically using the graph as a search index.
Yes. Right.
Great. Question 5. Does TyGraph support multiple edges of the same type between two vertices?
So between two vertices, and for each edge type, we can only have one edge instance.
Right. So that's a current restriction, but as product manager, I can tell you that in an upcoming revision, we will support multiple edges. Question 6, slide 28. So if you could go forward a couple of slides. If you aggregate information on an edge, will the searching benefit from also having the date information as vertices, um, as described earlier, as a relationship? So date on a vertex versus date on an edge. If you're aggregating, so oh right, so I think that's using a classic example for why you might um, want to have multiple relationships, like you have two similar things, events, but they took place on different dates. Um, so I think it's a question of where's the best place to put that date information.
Right. If we go with the schema on the right-hand side, then we cannot build like the indexes like this anymore, right? Because we cannot like create another edge to the edges. So
So yeah, and then it says if you aggregate, so that's the one on the right. So
yeah,
we kind of compressed everything onto a single edge. So if
right.
you aggregate the information, um, will the searching benefit if you have the date information as vertices? Um,
If we want to add those data information as vertices, then we hopefully will go with the design on the left.
right. So I think you have the two options. So if you think it makes more sense to have date as a separate vertex, then you're picking the one on the left. Okay, next question. Can you connect between user and event directly to IP? So the example where you had IP. So for example, IP to user to event to IP.
Yeah, so actually, again, that really depends on what you want to do, right? So if you do want to do analytics, such as like I want to find similar IP addresses, then of course we can just put the IP in the middle, make it connect to those event and users.
Yeah. I think what they're asking is, so all the schemas you have are trees. Um, like you don't have any loops. I think they're saying, could you make a triangle like in the top? Just put an edge directly between IP and edge type. So you have now a triangle. Can you do that?
Um, Sorry, can you say that again? I
So
couldn't
let's say
imagine.
we take the one on top
Mhm.
and we add an additional edge type
Mm.
between IP and event type. So now you have a triangle there. And the
Oh,
answer is yeah, you can.
yeah, of course.
Um, yeah, we were offering sort of a minimal design, but you can, and we do, particularly people put on, sometimes we think of those as shortcut edges when you've done some analytics and you want to find, I found an interesting relationship and I want to put a shortcut edge in there. We do that frequently. So,
Yes,
or you
it's kind of like we trade the memory space for the performance, right?
can,
Actually, in this case, we can also connect everything with everything. Then, of course, we have the best performance, right? Because everything is within one hop, one step. But the consequence is just like we will like it takes more memory to do that, right?
mhm. Yeah, so it's a trade-off with you can, so that's basically the analogy to what in the relational world they call denormalizing your data, where you have redundant information because it's more convenient to have it more easily accessible. And so you can do the same thing with graphs. You can denormalize it so that you have multiple ways to get the same information. And I think the following question was kind of asking the same thing,
Yeah.
um, but in a different way, a different sort of detail. What if you want both user centric and event centric? So you kind of like this center model and you kind of like the one on the right, both of them, because you have different queries.
Hmm.
And so I think you can basically accomplish that by putting those additional edges we talked about. You can make a full complete graph where there's an edge between every pair.
Hmm.
It's just having redundant information, and it's certainly possible.
Yeah. Right.
The next, the person who had the initial question about the languages was just sort of explaining a little bit more.
Oh,
Uh,
yeah. Uh,
so,
oh, yeah, please. Oh,
so what he meant was every value is given, say, 30 times because you have 30 languages. So you want to just have every string value is has a set of 30 values for 30 different languages.
right. So actually, it's not necessarily to just connect the like say language or transaction to the leaf nodes, right? We can also connect to the like a state level or even country level, right? So it's very flexible.
Mm-hmm.
So in that case, if each city has different transactions, you can just connect the transaction to the city, or each state has different transaction. You can also connect the transaction into the state like this,
Yeah.
right? So it's very flexible.
So I think one thing is, so just looking at the names of the places. So sometimes we have names of places given in different languages. So name is actually an attribute. So rather than being a single string, it could be a string array. We have lists in our schema. So we didn't talk about attribute types. We just talked about whether you have an attribute or not. But in TigerGraph language, we have a wide range of data types, numeric and string and Boolean, of course, but then we have compound types, lists and sets and maps. So, and it's really the map is really useful for, we didn't talk about generic vertices or edges. So that is how we can support the flexible schema where you don't know all the data types in advance that you want. So the sort of the hybrid or partial schema mode. So you can create generic vertices and generic edges, but through the use of maps to hold their attributes, and also define they can connect to anything. Um, so there was somebody asked the same question that was asked before about multiple edges. And there seems to be one more. Somebody's sort of asking if follow up to the bill of materials question, and about the color hierarchy. So I think this is going to be our last question. And then if you do have any more questions, please, you can send them to us at chat. Shinyu and I are available. Our email addresses are pretty straightforward. You can Victor at TigerGraph and Shinyu at TigerGraph. Yes. So the follow-up question, yes, but you could have the search index as a clear index and then reuse it to represent multiple nodes, which will increase the number of traversals instead of making it part of an index, especially in situations. So it sounds like the person is talking about a sort of a reusable index, but in exchange for increasing the number of traversals. So I think we were trying to reduce the number of traversals. That was our goal. I think, and I didn't 100% follow that question. So maybe if Paulo wants to email us later, we can cover that. So if you can go to the end, Shinyu, with the closing material. So our next webinar will be just next week on how to build innovative applications with a native graph database. So we are going to start to look at some interesting end use cases. So rather than talking about specific techniques, how you can build real applications, and we'll take a close look at the Customer 360 Starter Kit available at TigerGraph Cloud. Also, we have some graph gurus coming to you, and that is where we have some of our experts in cities around America, and we're going to start doing them in other countries too. So we have an event coming up in Boston next week, as well as one in the San Diego area, La Jolla. So if you are in one of those areas, we would love to have you. Just go to the TigerGraph website to sign up. And lastly, we mentioned TigerGraph Cloud. You can try TigerGraph for free. You can download the product for free. And then we have websites, of course, where you can find more developer information. We have our discussion community. Next slide, please. TigerGraph Cloud, we have online demos. You can download a version for free. If there are previous graph gurus have examples which you can try, and we have an online chat forum. So if you have follow-up questions, that would actually be a great place to go. And thank you very much. Again, we appreciate your time. This one went a full hour because there were so many questions from both Shinyu and everyone at TigerGraph. Thank you for your time.